So this video lesson is looking at friction. So specifically looking at friction forces. So when we've looked at friction forces before, we know that friction forces are FF. We can use to stand for friction of any kind. Okay. And we've also talked about it being FK or FS. So FK and FS are our two specific types of friction forces that we're going to have a look at in this video lesson. And so we're going to just start with a sort of quick definition of what friction actually is. So in physics, friction is a force that either So friction is a force that does one of two things. So it either prevents a stationary object from starting to move, and so this one is called static friction. Okay, and so in this one, we're dealing with a stationary object and we're preventing it from starting to move. Or friction is a force that resists the motion of an already moving object and slows it down. So this is kinetic friction. So with kinetic friction, we are looking at an already moving object and we're resisting its motion. Okay. So we are going to start by looking at static friction. And so static friction is represented by Fs. So if we start with static friction, so static friction is brought to us by Fs, okay? And the equation, so there's an equation to calculate static friction, looks like this. Our Fs is equal to something called mu s times Fn, okay? We can rearrange this formula, and this formula just gets rearranged as mu s is equal to Fs divided by Fn. And this formula or equation is actually on your formula sheets. It's not a formula that you need to memorize, but it is a formula that you need to know how to use. Okay, so let's talk about the three parts of this formula. Okay, so obviously Fs is our static friction. That's usually what we are trying to find. Okay, our Fn, we know from learning about different types of forces, is going to be our normal force. Don't forget that the normal force has to be 90 degrees to the surface. So it's 90 degrees in whatever direction the surface is. So 90 degrees from whatever the surface is that our object is resting on. Mu s, okay, so if you're trying to pronounce it, it's called mu. It's a Greek letter. Okay, it looks like a U, but it's got a little extra part to it. And that's because it's a Greek letter, mu. Okay, and this is actually called the coefficient of static friction. Okay, this coefficient for static friction is a constant value for individual surfaces. And objects. So this coefficient of static friction is different depending on what object or surface we're looking at. But if we are looking at the same object or the same surface, its coefficient is going to be constant. So its coefficient will not change. What that means is that we can actually look up values for coefficients, or we could be using our static friction and our normal force to calculate the coefficient. Some important things about this coefficient, I'll just get a new color here, is that it has no units. Okay. It is always positive. And it is always less than 1. So our mu s has no units associated with it. It is always a positive number, so it can never be negative. And it always has to be less than 1. So it is a decimal value, always. Okay. When we're looking at Fs, so the static friction force, so Fs, it's the maximum force to keep an object stationary. Okay. What that means is that Fs is the force that's required to just get the object to move. Okay, so Fs ends up being exactly the force that we need to just get an object to move. Not before that, but as soon as the object starts to move, that's what our static friction force is. It's that instant right before. It's the maximum force that's keeping the object stationary. As soon as we can get the object to move, then we've gone above our Fs. All right. Just another reminder as well, the units for forces, of course, are going to be newtons. So our Fn is going to be measured in newtons, and then so is our Fs in newtons. Okay, our other type of friction force is kinetic friction. And it's brought to you by FK. It also has an equation. And its equation is going to look similar. So our equation for FK, so we actually have our equation that FK is equal to something called mu K Fn. And we can rearrange that. We can say that mu K is actually equal to Fk divided by Fn. It looks almost the same as static friction because it's the same type of equation. The only difference is that now we are dealing with kinetic friction rather than static friction. And so we use a K subscript instead of an S subscript. Okay? Kinetic friction is for an already moving object. Kinetic friction is what's slowing down that already moving object. Okay. Now, as well, our mu K is our coefficient. But this is a coefficient for kinetic friction. It has all the same parameters as mu s. So it is going to be no units. It's going to be positive. it's less than 1. But there's one other parameter for mu k. And this new parameter is that mu k is always less than mu s. So our value for mu k can never be larger than our value for mu s when we're dealing with the same object and surface. Okay, so if we change the object and the surface, sure, our mu k can be different. But if we are dealing with the exact same object and the exact same surface, the mu s for the object will always be larger than the mu k for that object. Okay, and the reason for that, and you might have heard this saying before, it takes more force to start an object moving than to keep an object moving. And you may have actually experienced this in your regular life. When you are thinking about maybe your car has broken down and you have to start pushing your car. If you stand on the back of your car and you have to push on your car, it takes a lot of force to get your car to start moving. But once you have the car wheels moving and turning, the force that you need to push on it with to keep it moving is less. So you need a lot of push to get it started. Once you get it started and it's already rolling, then it's easier to keep pushing. So you don't have to push as hard. Okay, and so that's the reason as well why our mu k is always less than our mu s, because static friction, so our Fs, is always going to be bigger than our kinetic friction force. Okay, so it's going to take more to get an object started moving to break that static friction than it will to keep the object moving, so to overcome that kinetic friction. All right, so we're going to do some examples with these friction forces. So we're going to do some examples with actual involving static friction and involving kinetic friction. So we're going to start with some examples here. Okay, so my first example, we are going to try and find the coefficient of friction for a 22 kilogram box that has just started moving across a floor with a force of 62 newtons. Okay, first thing I want to do is pick out some information from my question. So I know that the mass of my box is 22 kilograms, and I know that it's moving across the floor with a force of 62 newtons, and I know it's just started moving. That's how I know that I'm going to be dealing with static friction rather than kinetic friction. If it was kinetic friction, the box would have already been moving. Okay, so I'm going to draw us a system diagram, and we're going to draw a free body diagram to have a look at this. So I've got my floor here, and I've got my box, and I'm pushing on the box. And I've got my motion. I'm going to have it moving to the right. It doesn't say, but I just decided to make it move to the right. And the motion just started. Okay. So when I draw my free body diagram, I know that I've got an Fn going up. I have an Fg that's acting down on the box. I know I've got an F applied. And I've got a static friction force now. And my static friction force is opposite my motion. Okay, so the question asked me to find the coefficient of friction. I know now that I'm looking for mu s. So my mu s formula is that mu s is equal to Fs divided by Fn. Okay, so I need to have Fs, and I need to have Fn. Okay, now from my question, I know for sure that my applied force is at 62 newtons, and I can definitely calculate my Fg, because my Fg is going to be mg, and the mass of my box was 22 kilograms. G is 9.8. So my Fg is 215.6 newtons. Okay. Now, F applied and Fg are not in my mu s calculation, but since I know that the movement has just started, that means that the box is really stationary. And so I actually also know that my Fs must be the same as my applied force. And then I also can say the same thing for my Fn. My Fn must be the same as my Fg. Okay, so then when I plug this into my formula, my mu s is going to be my Fs, which is my 62 newtons. And then I'm going to divide that by my Fn, which is going to be my 215.6. So I'm going to get my mu s is going to work out to 0.29. So again, we have no units for mu s, and we're using two significant figures because that's how many significant digits we had in our original numbers. So we're calculating that mu s for our box. All right, let's try a second example. So in this next example, I'm going to be dealing with a piano. So a piano is pushed with a force of 30 newtons, not 3 newtons. And we're using that decimal place there to say that this has two significant figures. And pulled by a rope with a force of 35 newtons. So we're pushing and pulling this piano. And it just starts to move. The piano has a mass of 92 kilograms. And this question is going to ask us to find mu s, which is nice. It's telling us right away, even though we could tell from the fact that it was just starting to move, that we're dealing with static friction. Okay, so we're going to start with a free body diagram. We should never start a forces question without thinking about a free body diagram. So we have this piano. It's being pushed with a force of 30 newtons, and it's being pulled with a force of 35, and it's just starting to move. So I know my piano must be sitting on the floor, so it's got an Fn. I know it has a mass, so it's got an Fg. It's being pushed with an applied force and pulled with an applied force. The pulled by the rope is going to be my tension. The pushing of the 30 newtons is my F applied. And then I know static friction must be what's keeping it in place. So then my motion, I've decided, is going to be to the right. You could choose whatever direction you want, as long as your T and your F applied are going to go in the same direction as the motion. So in order to calculate mu s, I have to do Fs over my Fn. Now, just like the last problem that we did, my Fn and my Fg are going to be the same. And so the nice thing for that is that my Fg is really mg, and we're dealing with a piano. It's 92 kilograms times my 9.8. And so that's going to give us 901.6 newtons. Okay, but unlike the last problem, I don't have my applied force just opposite my Fs. I have a tension and an applied force equal to my Fs. So that means my Fs must actually be equal to my F applied plus my tension. So my applied force was 30 newtons and the tension was 35. So I'm getting a total there of 65 newtons. So then I'm just going to plug that into my mu s formula. So mu s is going to be my Fs, which I calculated to be 65. And then my Fn, which is calculated at 901.6. So we're going to end up with 0.072 for our mu s. Again, there we've got two significant figures because that's what was given to us in the question. Our mu s is less than 1 and it's a positive value. Okay. All right, we're going to do, I think, one more example, and this example is also going to have to do with Fs. Okay, so third example, a 26, pen is acting up today. So a 26 kilogram desk is at rest on the floor. We're given that the mu s between the desk and the floor is actually 0.25. So we have the coefficient. One person pulls on the desk. With a force of 52 newtons to the east. And another person pulls with a force of 110 newtons to the west. And the question is, will the desk move? So we have a person pulling the desk in one direction, a person pulling the desk in the other direction, and we want to know if the desk will actually move. Okay. So we need a free body diagram here. So our free body diagram, we know that our desk is going to have an Fn. We know that it's going to be pulled down by our Fg. And we know that we have an applied force in one direction, and we have a second applied force in the other direction. Now, in this case, I'm not sure if the desk is going to move or not. So what I'm going to do is I'm going to decide which direction is going to be my motion. So I'm going to choose to put my motion going to the left. And since my motion, I've chosen it going to the left, my Fs is going to have to be going to the right. So there's static friction. Now, if you drew it in the other direction, so if you want to put your motion going to the right, then your Fs has to be going to the left. It doesn't matter which one you choose, but your Fs has to be going in the opposite direction to whatever you've chosen for your motion. Okay, so if we want to try and decide whether our desk is going to move or not, what I really want to do is to try and figure out what my Fs is and see if my applied forces can overcome my Fs. Okay, so one of the first things that I want to look at is what's my actual Fg. Fg has a nice formula all the time that we can always calculate. So our Fg is going to be equal to mg. So we know our desk is 26 kilograms. And we know our G is always 9.8. And so we end up with 254.8 newtons. Now the reason that I really care about Fg is because I really want Fn. So my Fn is going to be equal to whatever my Fg was. And I want my Fn so that I can use this formula. My mu s, remember, is my Fs divided by my Fn. Okay, and I want to rearrange that and solve for Fs because I actually have mu s already. So my mu s was 0.25. And my Fn was calculated to be 254.8. So my Fs is 63.7 newtons. Okay. Now, I didn't round for significant figures here because this is not the final answer. Okay, so I want to keep a few extra significant figures. Now, what I want to know is, will my applied forces overcome this 63? So will my applied forces overcome this 63.7 newtons? And to do that, I need to find the total of my applied forces. And so since I decided that my left was my positive direction, that means I'm going to take applied force number 2 and subtract applied force number 1 because it's going in the opposite direction. So applied force number 2 was my 110 newtons. Applied force number 1 was 52 newtons. And so I'm going to get a difference of 58 newtons. Now, since my F applied total is less than my Fs, the desk won't move. Okay, so the thinking here is that our static friction force is the force that we need to overcome to get an object to move. So if we are pushing and pulling on this object, we are only pushing and pulling with a total applied force of 58 newtons, which is less than the 63.7 barrier. And so we will not get this desk to move. The desk is going to stay stationary. It's not moving at all. Okay. All right. That's it for friction forces. There is some practice to work on to practice a little bit more with friction forces. And that's the end of this